Hello all. This presentation is about the automated logistics use case. And we will start the presentation with a use case description because the needs of verticals guide operators and technology developers in designing and implementing solutions. And then we will focus on the components and the technologies beyond 5G that will be implemented to fulfill the requirements of automated logistics. So, the biggest issue that appears in the field of logistics and specifically in the environment within a warehouse is when we try to change the position of products. The products are placed in specific areas inside the warehouse, depending on their type and the environmental conditions that are required. For example, some may require special temperature or humidity. But when the products are being prepared for shipment, they are moved to different places. For example, you can imagine that during their stay in a warehouse, each product can change position more than 3 times. So it is important to design solutions that focus on the elimination of the waste of time for unnecessary movements due to wrong location of the product or incorrect route selection within the warehouse. To design the solution, the technology provider must take into account challenges that may arise. For example, it may be difficult for data to be processed in real time for critical events and to be solved in a quick manner. Data exchange mechanisms use their own modeling and SIMs, and this takes time to make the end-to-end system interoperable. And the large amount of the IoT devices that should be installed is also challenging because we should choose the proper place to be installed and a large amount of data to be shared. Taking into account all these aspects, it seems that advanced communication technologies combined with proper UEs and different devices could allow us to propose useful solutions. 5G and beyond 5G networks are now introduced not only to redesign the production line, but to enable operating models with networking characteristics that could enable added value services. Therefore, by utilizing the high network performance and combining it with the cloud computing, we can implement services that they offer a high degree of autonomy, fast information processing between UE and its environment, and additionally, introducing AI cloud would increase accuracy on the decisions, data analysis, and also allow a faster response. To put all this into motion, the technologies and components to be developed were divided into 3 categories, as you can see here: applications, network, and KPIs monitoring. Applications focus on how UEs can improve both the production process, for example, in our case, reducing delivery times, and also employee safety. By eliminating the needs for employees to manually transport heavy goods, we could minimize the risk for injuries. About the network category, we could focus on exploring and testing the integration of large-scale extreme IoT-Edge-Cloud scenarios based on 5G standalone technology. And finally, KPIs monitoring components will ensure network performance and be used in slicing mechanisms that will be described a bit later on. Let's describe now each category separately. In this figure, you can see the network infrastructure that will be used. It includes the packet core and the RAN, based on 5G standalone Release 16 architecture. There is also a slice manager and the cloud infrastructure where a service orchestrator could be installed. The UE that will be used, as you can see here in this photo, is a robotic vehicle equipped with cameras and sensors. Several probes are also installed to collect network performance measurements. We will see later on how these measurements could be used, not only to identify if the network performance is the proper one, but also to design an optimal service slicing mechanism. One of the key network capabilities is the change of slice. Modern networks require increased resources and at the same time a large amount of computing power to process the volume of data. So slicing mechanism will be designed which will automatically assign resources to the end user, ensuring that there will be no unnecessary resources allocation, allowing in this way sustainable network processes. Currently, there is a slice manager installed in the network, which is able to send information when there is an update in the existing slices or after it is requested by the service orchestrator that will be installed or any other authorized system. The protocol used is HTTP and the methods are post, put, and delete in order to create, update, and delete slices. The mechanism allows the robot to communicate and interact with the network by requesting resources, slice change, or ask for information. So the UE, the robot, in our case, is not just a component that a user can utilize, but it could be considered as part of the end-to-end architecture. This mechanism, the slice change mechanism, the existing one, is planned to be upgraded. Real-time data about the network performance will be used to detect the need for slice changing. This data will be collected by using the proper components. So my colleague Panagiotis Verius will provide more details about these components and the monitoring tool that will be used.
Yes, the commercial monitoring tool installed has already started gathering test data from some test cases that have been implemented in a part of the network. These are presented within the commercial product with graphics and also provide information on different variables like frame loss, frame delay validation, jitter, we'll see later. So depending on the condition of the network for the automated guided vehicle endpoint, there may be a need to include or add more slices to the underlying 5G network. So the performance of the applications running on the AGV robot will be more productive and reliable. So we can go to the next screen. This data and other data gathered will be available and in the graphics interface of the commercial application, but as well, we are already in contact with UMA people that they're now introduce us. This data will be provided, taken by the ELCM environment, 6G path, and used within the overall environment as we consider appropriately. Here's just a snapshot of where we see the overall availability, overall loss, latency, and jitter. And as I said, the aim is to produce scenarios where there will be congestions or other problems within the network from the use of the automated guided vehicle, which will trigger the expansion of slices within the network. So you can continue now.
Thank you. So the last category is the application category, equally important as the network and the KPIs measurement. Cloud services will be developed to optimize robots' performance. The robot will move autonomously on the area of the warehouse. However, in case of an unexpected situation, a human operator should be able to take control of the robot. Additionally, the operator will be able to direct the robot to perform specific tasks apart from those that will be programmed in advance. And finally, data will be collected and analyzed in real time, such as network performance metrics that are provided by the robot. And there will be a check of the correct data reception from the robot sensors and cameras. And as I said before, these applications will be installed in the cloud because this architecture will allow the faster response of the applications. Finally, here you can see a summary of the network capabilities. And please let me also mention that since we are talking about a warehouse and this implementation will take place in a large area, it would be preferable from our side to investigate how handover between G node Bs combined with slicing could increase the opportunity to provide better services. For example, apart from slice changing within a cell, it would be a good idea to investigate how this would also be combined with different cells in the same area. So these are some ideas that beyond 5G technologies allow us to test in such demanding environments. Thank you very much for your attention.